Greetings everyone and welcome to this new video on how to perform a one-way analysis of variance in R. First of all, we'll start by loading a few libraries. Tidyverse library is an amazing package which contains lots of functional dependency libraries. This summary tool library will help us to get a very nice structured summary statistics table. The ggpubr library will help us to plot beautiful plots. The emmeans library will help us to compute estimated marginal means of our analysis of variance. And the report library is great to write automated statistical reports, which will save you a lot of time. So for the purposes of this tutorial, we'll be using the tooth growth dataset. So from the datasets package, and basically if we run a query on the tooth growth dataset, this will give us a description of a dataset. So this dataset is a response of the length of odontoblasts in 60 guinea pigs. And each guinea pig received one of three dose levels of vitamin C, 0.5, 1, and 2 milligrams per day. We are not concerning ourselves with the delivery method for the purpose of this video. We'll cover that later in a two-way analysis of variance. So once we have loaded this dataset and stored this in an object df, we can get a structure of this dataset, which will help us to get an idea of the type of data. So the len stands for the length of the tooth of the guinea pigs, and this is a numeric variable. So this will be our dependent variable. Supplement, we are not going to concern ourselves with this variable for the purpose of this one-way analysis of variance. We will concern ourselves with the dose. So as we see here, we have three dose levels, 0.5, 1, and 2. However, R has coded it as numeric, and rightly so, because it has detected that these are numbers and therefore it has coded as numeric. However, we want this to be a factor variable with three levels, 0.5, 1, and 2. And we can do this very easily using this line of code. So whenever we put $, we are extracting a vector or a variable inside this object. So the variable dose is inside the data frame object, which we have stored here. And we are going to convert it into a factor level using this function as.factor. So we'll run this line of code and again run the structure function or str function. And now we see that it has been coded into a factor with three levels, which is perfect. This is what we want. Now we'll attach the data set to enable easy calling of the variables. And let us get a visual idea of how the data set looks like. So we can do that using the head, which will give us the first 6 rows of the data. And we can see that the length of the tooth is given here and the dose of vitamin C is given here. Let's run the tail, which will give us the last 6 rows. And this looks fairly okay. So now, before running any type of analysis, we would first like to get some summary statistics. So we'll use that using the df summary function from the summary tools package. And this is a pipe operator. You can find that in the dplyr package, which is inside the tidyverse package. So basically, you can string lines of code together very conveniently using the pipe operator. So the df is of course the data frame object. Now we want to group by dose because we are interested in seeing the length of the odontoblasts grouped by dose. And we'll store this in a SUMM object we'll name that SUMM, and that will actually be enabling us to call upon this object using the view function to get a visual representation of our data. So as you can see, this is a very simple, straightforward single line of code, and here we have our summary statistics. So you can see that for zero point 0.5 mg per day of vitamin C, the mean tooth growth was 10.6 with a standard deviation of 4.5. You can also see for 1 mg per day, it's 19.7, so quite a large increase. And for 2 mg per day, it's 26.1, so uh, a higher increase in tooth length. So now we want to test whether this result is statistically significant, that the mean tooth growth actually is higher if we increase the dose. So we would like to run an analysis of variance for this. But before running a parametric analysis of variance, we would first like to check some assumptions. The first assumption we'd like to check is that of independence. The observations in each group are independent of each other. So if these observations were paired, that is repeated measures, we would use a repeated measures analysis of variance. In this case, the observations are independent, so this assumption is met. And the observations within groups are obtained by random sampling. We hope that the authors have used a random sampling method. The second assumption is the assumption of normality. If this isn't fulfilled, then we would go for a non-parametric test such as the Kruskal-Wallis test. Let us test the assumption of normality using the Shapiro-Wilk test. And the Shapiro.test is the function which is included in the base package. So you don't need to load a separate package or library for this. And remember that a significant p-value for the Shapiro-Wilk test indicates that normality is not present. The data are not normally distributed. So if the p-value is not significant, that means that the data is normally distributed. And we can see that all of these three p-values for each dose level are not significant. So that is good because now we know that the data are normally distributed. The third assumption is that of homogeneity of variances. That is, the variance of the populations from which the samples come from are equal. So we can do that using the Bartlett test for homogeneity of variances. And again, like the Shapiro-Wilk normality test, if the p-value is not significant, that means that this assumption is met and we are good to go using the one-way analysis of variance. To perform the one-way analysis of variance, we use the AOV function, which is included in the base R package. And similarly, for the t-test, even in the AOV, or even for regression or any other analysis in R, the variable on the left hand side of the tilde is always the dependent variable, and the variable on the right hand side of the tilde, or the variables, are independent variables. So we'll run this AOV function and store the results in an object called fit. We can automate the statistical reporting using the report function. And here we see that the p-value is significant with a p-value of less than 0.001. That means that the result is very highly statistically significant. The eta squared is also large. That is, eta squared is the effect size, which is used in analysis of variance. And this function also gives us how it has come to this conclusion of that this is a large effect. So this is using the Fields 2013 recommendation. All right. Now, the estimated marginal means. So the emmeans function can be run from the emmeans library that we'll store in an object em. So to run this emmeans function, the model or the fit of the analysis of variance needs to be called first, and we need to specify whether we want pairwise comparison. That means, do we need the difference in estimated marginal means between levels? And yes, we do. We want to see whether there is a how much difference there is in between say dose of 2 milligrams per day minus 1 milligram per day, or minus 0.5 milligram per day. So what is that difference in the tooth length? So that is what we mean when we say when we write this pairwise argument inside this function. And we'll, as with the AOV function, we'll store this in an object EM. Remember that storing results in an object is very handy so that we can call upon this object later on, as you see here, so that you don't have to write this line of code inside the bracket, which will get very confusing in more complex analyses. So after we run this function, we will get the summary for the estimated marginal means, and we can see the mean. So for a dose of 0.5 level, the estimated marginal mean tooth growth was 10.6. For 1 milligram per day, it was 19.7, and for 2 milligrams per day, it was 26.1. It is important to remember that for a one-way analysis of variance with no covariates, the estimated marginal mean approximates to the true mean. However, when we run a two-way analysis of variance, or when we run an analysis of variance with covariates or an analysis of covariance, this estimated marginal means will adjust for those other variables. So we'll come to that in later videos. We also get nice confidence intervals for our estimated marginal means. And here, because we have specified that we want to pairwise comparison as well, we get contrasts. So we get the tooth length of in guinea pigs with who have been given 1 milligram per day minus tooth length, average tooth length of guinea pigs who have been given 0.5 milligram per day. And this is negative 9.13, 2 minus 0.5. So this is negative 15.5 and this is negative 6.4. We also get p-values. For this, that means whether this difference is significant or not. So this is basically a post hoc comparison. And we automatically get a Tukey adjustment for p-value. So that is excellent because we don't need to manually correct the p-values for multiple comparisons. However, if you see, we don't get confidence intervals here. So we need to run another function conf_int, which is also included in the base R package. And we'll run that for the same object EM. And here we get the confidence levels. Now, if we want to plot these estimated marginal means with the 95% confidence interval, we can just run a simple plot function included in the base R package, and here we get the means with 95% CIs, and we can see that as the dose increases, as the dose of vitamin C increases, the estimated marginal mean of the tooth length also increases. And we can use the ggpubr package to get better plots than this. So the GG line package will help us to get the means. These are the raw means, mind you, these are not the estimated marginal means. However, in this case, in the one-way analysis variance, as I've already mentioned, these are the same as estimated marginal means. But in two-way analysis of variance, we would be needing to see the estimated marginal means and not the raw means. So here, this graph is the same as this graph. And we see the confidence intervals, and we can see that as the dose increases, the means also increase. And we can also get box plots if we wish, if the data are not normally distributed, and if we run non-parametric tests, box plots might be better data visualization tools. So that's it for this video. Thanks for watching.